All right, activity 3. I don't think it's actually activity 3, but I'm going to call it activity 3 because it's convenient. All right, so to start then, we're talking about electric fields. So we have field lines. Draw arrows specifying the direction of the electric force on an electron. Electrons are negatively charged. Placed at A, B, or C, using the length of the arrow to indicate the relative strength of the forces. All right. So, you probably haven't learned this yet, but I'm going to show it to you anyway. So if you have a large infinite plate where it's positive, and you have a large infinite plate which is of negative charges, this is a parallel plate capacitor. And the electric field between it goes straight. One of the nice things about parallel plate capacitors is you get a very uniform electric field. So every now and then you might have heard about, hey, you have an electric field that goes from like left to right. But every time they talk about how to make electric fields, you see charge particles and everything's radial. It's like, how do we get straight electric fields? Well, parallel plate capacitors is how you do it. And the way you think of it is you have a plate over here of infinite charge, you have a plate over here of negative charge, and it makes it really easy to visualize that if I have an electron right here, it's going to be repelled by the negative and attracted to the positive. So it's going to go this way. So every time I see an electric field, like these guys right here, I immediately think, oh, positive plate right here, negative plate right here, source, which is a source of electric field, sink, which is a sink of electric field, bam, arrow from source to sink. So then for B, which I'm going to do first because I think it's the easiest, we have an electron right here. This electron is then going to be pulled towards the positive, and then it's the electric field density. Basically, if I draw a box of the same size, I'm going to say like this big right here. So I'm going to draw one right there. How many lines is it going to have per box? It's going to have 4 lines, which is going to be more than if I do it anywhere else. So this will have the biggest arrow, the biggest strength, which means I should probably draw it a little bit bigger. Okay, there we go. Now it'll make me feel better. All right, let's go to A. All right, so I have an electron here. So we don't actually have a line that goes through A, so I'm going to redraw it. Now, one of the things about electric field lines is they don't cross. Electric field lines do not cross each other. They can get close, but they can't actually cross. So that's why, to guess what A is, it's like, all right, A is between these two, kind of in the middle. So I'm going to draw a line in the middle all the way down to through here. And it's going to be going in the same direction. All right. So now I'm going to draw, this is the direction that the electron is going to go. It is going to follow the, it's going to be tangent to the curve. Tangent? Yeah, it'll be tangent to the curve. Same direction as the curve at this point here. So the force is going to be that direction. And then it looks like the density there is going to be a little bit less. So the arrow is going to be smaller than B. All right, so then we have C, which is right here. C, same idea. Now if we draw, I guess, tangent? Yeah, tangent line is the right word. Tangent line is going to be off this direction, just following the line. And if I draw the same size box I did earlier, we see that C is going to be stronger than A, but weaker than B. And just to reinforce the idea, the absolute value, magnitude, of B is bigger than magnitude of C, which is bigger than magnitude of A. So, yep. So when I see this, I go to, so the way, it's going to be tangent to the line, same direction as the line, any way you want to see it. So like for here, if you want to look at it this way, it might be easier. You draw a tangent line. At this side of the tangent line, you draw your positive plate. At this side of the tangent line, you draw your negative plate. And it's obvious then to see that the electron placed at A would then go towards the positive plate B. So don't draw all these extra crazy plates everywhere. And maybe draw a couple, maybe here. But just draw with the answer they're looking for here. You don't have to be as artistic on your homework as I am on the homework, or the lab. All right, use the arrows. Yep, I think we got that one. Now symmetry. All right, symmetry. Use symmetry to determine the direction of the electric field at the location indicated by the dot for each charge distribution, A through D. Okay, note there is no charge at the dot. It's just a it just marks the location. All right. So we're going to start here. So the way I'm going to look at this one is I'm going to look at a section like this. All right. So this section right here, it seems pretty reasonable that's going to create an electric field. Oh, it's positive, so it's going to be other direction. So it's going to be a source, so it's going to push in that direction. It's supposed to be towards the center. It's just a bad picture. And then here is also going to push towards the center. So at the center here, we're going to have from here, from the left side, we're going to have it push this direction. From the right side, we're going to move this guy over. It's going to push that direction. They'll cancel each other out exactly. And you can say that for any sections of the pie you make here. And so what's going to happen is there's going to be no net electric force at the center. And then what's interesting about this specific shape then is, erase this, there's not going to be any net electric force anywhere inside the circle. So if I do the same thing, look at the same concept here. So we have let's say we're looking at this point right here instead. So we have this portion right here and this portion right here. We're going to compare the two. So this one has a positive charge and it's going to push this direction. Well, this section is going to have a lot more effect because it's very close. But there's only a small section that's doing the pushing. This section is going to be very large, but it's farther away, and it's going to push the opposite direction. Well, it turns out that the trade-off from the distance and the distance on one side and the excess charge on the other side, and that's assuming this is a I think this might only apply to a sphere. I'm going to say this only applies if it's a sphere. Are exactly going to cancel each other out. This is drawn as a circle, but I'll assume 3D sphere. That's what that's the concept you're going to have. No, it applies to a circle too. It also applies. Nope. Say it applies to a sphere, not a circle. This is a concept you'll see again later with when you talk about spherical conductors. So keep that guy in mind. It'll be useful later. But electric field, net. I guess I don't need to say it's a vector if it's 0. But I will anyway. All right. So now we're looking at the dot here with negative and positive. All right. So I'm going to draw the negative here. So it's going to create electric field like this. And then it's also going to create electric field on that side. And if I do this, copy paste, yes, taking the easy route. Do the same thing on the other side. All right, so those are all the electric field lines for that guy. And then if I just copy, maybe I can do this, maybe it'll be easy. Copy paste. These will be the electric field lines for the positive. Wow, this makes me feel really lazy. All right, so zooming in, you can kind of see. I'll redraw them just so it's a little bit more obvious. So we have an electric field line going in here, and we have an electric field line going out here. So at the point, we're going to have, this is the point, electric field to the left. So we're supposed to draw, you supposed to determine the direction of the electric field. So just the direction, not the magnitude. So E net, I'm going to put a B here so we know we're talking about B, is to the left at the dot. All right. Moving on to C. So we're going to use the same argument for C that we did for A, except this time there's a part missing. So these two sections are each going to cancel each other out, and all we're going to be left with is this section here, and it's going to have electric charges towards it since it's a sink. So these are all going to add up and cancel out and just create a net electric force going up. So E electric force net for C is up. So, yep, I believe that. All right, now for D. So let's see here. Let's start by assuming that these distances are the same. And so we're going to have, I'm going to draw this once, really nice. And I'm just going to copy and paste it. Probably shouldn't make them so big because I'm going to have a billion of them. There we go. Copy paste. Up. And I didn't want them all. Don't want those things. I'll just paste again. Paste. 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 And this one's going to be turned upside down. Copy, paste. There we go. And there's some too on the other side as well. I just don't care to copy them. There's some on the bottom right side. Oh, I missed part of the... That's okay. You get the general idea. All right, so let's zoom in here. So the two line charges are directly opposing each other, but one is 2q, one is 1q, so the 2q is going to win. So I'm going to write it down here. E net, or D, and write it a little bit nicer than me, is that way. Maybe say down and to the right. So, or you could just be like, bam, E net, because it's going to be dominated by the 2q line. Okay?